Hello, welcome to Chapter 12. Although the title to this chapter is more about tests and intervals, really the new thing that we're going to learn is about types of error and powers of tests. So although this title is more about tests and intervals, I'm going to review some of the concepts and go over them again. And it's going to feel a little reviewy. I'm going to say some things I've already said before. For this reason, you're probably going to read this more than you want to listen to it. It's a good review chapter to go over the idea of testing. Okay, so a p-value is really a conditional probability. If you hadn't thought about this before, it's operating and calculating a probability based on a current value or an assumed null hypothesis. So I've written a p-value down here, assuming, the null hypothesis of your proportion, the null hypothesis is that your proportion is 50%. Then we really are looking for the probability that you got your sample or something larger. This is going with a right-tailed hypothesis test. So remember, the p-value is a probability, and it's not just any probability. It's one assuming the null is true, because you're using the null to build your distribution. So what can we do with the p-value? Well, it's really up to you. So if you have a small p-value, you could look at this and be like, well, I guess I'm going to reject my null hypothesis because I've got some strong evidence against it. But how small is small enough? And we've gone over this before. You might look at something and think to yourself, oh, well, that's small, but is it small enough to be unusual? This is one of the reasons why statisticians like to report their p-value, not just what their conclusion was and what their level of significance is. Really, it's good practice to report your p-value, because what you might think is significant because you like to use 5% and other people might not necessarily, they might like to use 1, might be different for somebody else. So what about a high p-value? How high is high enough to not be surprising? So something like 10%, that's still pretty small, or maybe 8%, still also pretty small. You might think, oh, unsurprising needs to be at least 30%. And this is one of the reasons why I keep saying report the p-value, not just your alpha level, because a really large p-value is like, boom, hey, this is so big that, it means something. Usually we describe our rare event or our statistically significant event ahead of time. We use a threshold called alpha, also a probability that I'm going to go into grave detail today about what alpha is all about, because, well, we haven't had a whole lot of detail on alpha. So alpha is called the significance level, and you really are supposed to select your significance level ahead of time. The reason we want to do this is because, well, you want to be conscientious of people who might finagle their results or adjust their choice of alpha to force things to be significant. So I'm saying somebody might be like, oh, well, I did my test and I got 8%, so I'm going to pick my alpha to be 10%, so then it's significant. That's just bad science and very dishonest. So let's be ethical and natural scientific minds who, seek the truth rather than just what we want to hear. Okay, so a couple things. In case you forgot, couple common levels of alpha, 10, 5, 1, and 1.1% are also all very common. If you can get 0.1, you probably got enough. Well, you got more than enough. That's like hitting it with a sledgehammer when you could have used a hammer. And just as a reminder, if your p-value is smaller than alpha, we reject because it's significant evidence against your null hypothesis. And if your p-value is larger than alpha, then we fail to reject because you don't have significant evidence against it. You more or less have evidence towards it. Okay, so many statisticians report p-value rather than alpha because then the idea is if you report a p-value that you might not reject, other people might choose to reject it based on its size. It also is just good practice because then when people go to replicate your results, they can actually prove to themselves that they did it correctly and you did it correctly. So report the p-value. Yo. Now, one thing to be cautious about is that for large samples, or even small ones, unimportant, insignificant deviations could actually register as being statistically significant. One of the reasons this occurs is because when you're considering calculating things using statistics, and in particular using the sampling distribution, your standard deviation, whether it be for the mean, for a proportion, or for a mean, Oh man, I'm regretting my choice here, x bar. We'll use p hat. There, it's clear what I'm up to. Both end up dividing by the square root of the sample size. So when you have a large sample size, that means that your standard deviation is very small, which can make it seem like your spread is, well, your spread will be very tiny, which means things that are far away could look larger because of how big of a sample you have. Now, be careful. When it comes to statistically significant, it may not be practically significant, and there is a big difference between the two of these. If the consequence isn't enough for it to matter to your company or to your customer or to your individual employees, it's not going to matter at all. So just because it's significant doesn't mean it's practical. Please take note of the difference between these two, especially when you go to apply statistics to your real-world careers. When building a confidence interval, one of the ways we did this was using what are called critical values. I hope you remember that these are the Z's or T's that correspond to the cutoffs for the bounds of whether or not you are within the level of confidence. If you don't remember this, I'm going to draw a picture for you in a bit, so don't worry. So we used to do this using by hand methods, but you know, there are some other ways you can do this. So although we're really used to using the p-value, there are other ways you can design cutoffs, and that's using critical values and comparing them to Z statistics or T statistics. So here's a little bit about what this looks like. When you're looking with technology at p-values, it's, you know, the areas are easier to find. But if instead you wanted to, you could use traditional T. So on the left, I've drawn a picture of what a one-sided 5% critical value is going to look like. So this is associated with doing 5% in the right tail with 95% in the left. And I'm hoping you recognize that Z value or Z critical value from doing confidence intervals. Now, the two-sided behaves exactly like a confidence interval that's two-sided, and that's when you're looking at things like, well, the two-sided 5% will have 95% in the middle, and then alpha makes up the 5% in both tails. So really one tail for the two-sided has 2.5%, and both tails together make 5%. And that corresponds to, well, the 95% rule, which gives us a z-score of 1.96. And I just noticed that I have a little bit of a typo here. That should be negative 1.96 on that side due to symmetry. And the last thing to note is that alpha really is made up of what's left after your confidence level. If you think of the confidence level as a decimal and not a percent. Later on, I'm going to talk about it as a percent. So one thing to keep in mind is I just did Z, but the student T model has, well, a different shape based on every single sample size. So when you're calculating the critical values, it's going to be different for every single T. So it's important to recognize that when you're doing a left, it looks like, well, the one I have on the left, where your alpha is in the left tail, and you'll have to find the critical value for each and every distribution depending on your degrees of freedom, which if you remember is 1 minus your sample size. Sorry, 1 minused from your sample size. I misspoke there a little bit. And you get half of alpha in each tail. Now, I do have a video in Chapter 11 on calculating T-scores. If you have not viewed that video because you did not think you were going to use it, you might need it for this section's homework. Since we call these critical values, we usually call the areas critical areas or cutoff regions or rejection regions, since if you fall into the alpha region, you reject your null hypothesis because you'd be smaller than alpha. Yay. Okay. So confidence intervals and hypothesis tests are really one and the same. We've done this before. Previously, we've looked at values and asked, are they in our confidence interval? And if they were, you could say things like, oh, well, that's a perfectly reasonable value for the mean. It's in the confidence interval, because the confidence intervals do things like estimate the values of the parameter. So for instance, if you were doing one for means, you'd be giving possible values for the mean. Then when you go to do your hypothesis test, you could note whether or not that value was in the list of possibilities, and you'd know how confident you were. So the correspondence between these two is actually one and the same. So although a confidence interval gives you a list of possible values, the hypothesis test allows you to test for specific ones. And it does it in the same manner. I'm hoping you notice that we use the same distribution, the sampling distribution, and that's why these correspond with each other. So how do you relate alpha to the confidence level, C%? Well, it's 100 minus C%. Those are the same thing. So if you know alpha, you know the confidence level for the confidence confidence interval associated with that hypothesis test, or if you know the confidence level, you can find the the level of significance associated with your test. So be careful when you're doing a one-sided test. This looks a little bit different. You end up with 1/2 of it unbounded. So if you're doing a left-tailed test, you will know that it's a upper value and everything below it. If you're doing a right-tailed test, you'll have a lower value and everything above it, since you're just doing above or below, shading to the left or shading to the right. And then the two-sided test is all the values in between. So sometimes when we're reporting a two-sided confidence interval, we really only need one side if we think it might be larger or smaller. So although this hypothesis test can tell you about how these values differ from the hypothesized value, it doesn't say by how much. So be careful, the corresponding confidence interval information actually is a little bit more informative. So what I'm saying is that you might do a hypothesis test and you're like, oh, well, failed to reject, it's something bigger. Well, how much bigger is it? Is your mean like 20 times bigger, or is it just like 1 or 2? And the confidence interval can actually give you a range of possible values for what your mean actually is. So it doesn't hurt after you do a hypothesis test to get more information by doing a confidence interval. You also can approximate a hypothesis test by looking at the confidence interval. So for instance, if you do a hypothesis test and you have like your null hypothesis is that P is like, I don't know, I'm going to pick something, we'll say like 1/2. If we have a confidence interval, like something that goes from like, I don't know, 0.43 to, I'm making these up, please don't like think this is serious math here, 0.67. Oh, I don't want to do a 6. Let's do a 6. Nope, no 6 for you, no 7 for you. This is not working. 10. There we go. Sorry. So the idea is that, oh, well, you know, P is in this interval, my hypothesized value, so we would actually fail to reject in this case. However, if you had a different confidence interval, so let's say that you didn't necessarily have this first one, and you got it, and you got something like, I don't know, 0.63 to 0.82. I'm totally making these up. These numbers don't matter. Oh my gosh, this is, you know, all above my hypothesized proportion. And not only that, but my proportion is not in this interval, which means it's in the region of failure or the region of rejection. So you would actually reject this. I keep saying region of failure and rejection because it's outside the hypothesis value. It's in that 5% of, oops, I'm not in there. So it's considered an abject failure, unfortunately. Let's do an example of this rather than me just futzing and making up numbers. So suppose you look at shopping patterns from a small convenience store who randomly sampled 20 purchases from yesterday's sales. This is an example we used previously. The 95% confidence interval was $35.586 to $54.34. Is there evidence that the mean purchase amount is different from $40? Well, $40 is in there, so I'm going to go with no. There isn't evidence that it's different. In fact, it very well could be that the mean is $40. And that's exactly what the answer says. So at the 5% level, so remember, this is my confidence level, then my alpha is going to be, you know, the percent left over, 5%. We failed to reject the null hypothesis. The 95% confidence interval contains the $40 as a possible value for the mean. Sorry, I said plausible there. Whatevers. There is no evidence that the mean purchase amount differs from $40. It appears to be that it isn't. Okay. So this is all well and good, but it might be that what you did is wrong. Let's get to the new part of chapter 12, errors. So there are two ways that you could make errors or make mistakes when you're doing your hypothesis test. You could start out with the idea that, oh, my null hypothesis is true, but you accidentally reject it. So this is rejecting a true null. Or you could have a null hypothesis that's false, but you fail to reject it. So you failed to reject a falsehood. So we call these the false positive and the false negative. And this is mostly used in medical testing. And these are known as the type 1 and type 2 error. And depending on the situation, one of them is usually more severe than the other. I mean, don't get me wrong, they're both bad, but Um, in the medical world, having a false positive, so accidentally getting extra treatment for something when you didn't need it, is much more better than having a false negative, so you're actually sick and need treatment and they just send you on your way. So in the medical community, they're much more concerned with the false negative or type 2 error than they are with the type 1 error. But there are different situations where one of them is worse than the other, or they're both awful, which is the case that sometimes happens. So just keep that in mind. Generally speaking, most people settle on the fact that the alpha, is it the alpha error? No, the beta error is worse. Or wait, I don't even know. That doesn't make sense. Ignore what I just said. Let's look at a diagram of this to help make sense of it. So along the top, I have the truth. So my H0, my null hypothesis, is actually true. And on the bottom, you know, I correctly failed to reject it. That's the good stuff. But there is the possibility that you accidentally reject it when you shouldn't have because it was actually true. That's the type 1 error. And then the type 2 error is, oh, my null hypothesis is false, and you reject it, which is good because it was false and you should reject it. The type 2 error would be, oops, I failed to reject something that was untrue. Whoopsie-doozles. And this is why I kept saying alpha earlier. As it turns out, that the level of significance you're setting at the beginning of your test is actually the probability that you'll make a type 1 error. So by selecting alpha, you control what the type 1 error is going to be. So what about the type 2 error? Well, let's look at an example. So here's another diagram of the type 1 and type 2 error. And I'm just now noticing that I have a mistake on this. It should be the defendant is, you know, not innocent. Not innocent. Oh, that doesn't look like words. And these should have stars, which aren't showing up, so that's fun. Don't worry about that for now. So the idea is that only the defendant knows if they're innocent or not. So if you're innocent and, you know, you end up getting held guilty, you end up being false imprisoned, and that's the type 1 error. The the correct decision would have been, hey, you're not guilty, go home, be good. Don't do bad things or get caught doing them. The defendant not innocent goes along with the idea of, oh, we reject, that person's guilty, that's the correct decision. They should go to jail, they are not innocent. The type 2 error in this case would be, you know, letting go the bad guy. So generally speaking, the presumption of innocence in the justice system, different things that get impacted by different people. So the type 2 error, which I have pictured over here with the, you know, not guilty verdict, is the idea that an innocent person would be arrested, and that would be bad, impacted by your evidence, which is the impact of testimony. And then the type 1 error would be a guilty person is arrested and jailed. Sorry. Yeah, because then this region right here would be the type 1 error. The innocent person gets arrested, ends up going to jail. So guilty verdict. And then this area right here is, woo, you know, guilty person goes free. So this is the 2. Woohoo! And then this is the 1, to clarify that for you on the picture. So I think both of these are pretty bad. I hate the idea of a innocent person rotting in jail, but I also hate the idea of a wicked deviant going out and wreaking havoc upon our society when he could have been jailed. So I personally think both of these are bad. I don't know what you think, but feel free to share. We call the power of the test the ability to detect a false hypothesis. So power is actually the probability that you don't have a type 2 error. So we assign the letter beta to the type 2 error, and then we call power 1 minus beta, which I've written down below. So there's some problems with this calculation, and it's the idea of how big of a difference does it have to be for this to matter. So if you've watched the animation I have on this is a little more informative than what I'm about to go through. So you can actually skip like the next couple slides, because I'm going to go through exactly what the animation covers. Okay, I have a mess of a drawing down below, but don't worry, I will explain it to you. So the biggest issue with the types of errors is that the only real way to fix them is to reduce sample size. So down below I have the green distribution, which is the P0 or null hypothesis distribution. This is the one you go into your test assuming is the truth. And then next to it I have the red distribution, drawn rather terribly. That is the actual truth distribution because its center is actually P, the mean of the proportion distribution. So as you look at this, I'm hoping you notice the areas I have shaded and that for some reason have red dots all over them that I can't get to erase. So the green region is your choice of alpha. It's your type 1 error or your reject a true null hypothesis guy. Because the idea is that if you fall in the area around alpha, you should be rejected, as in, no true H naught. And that falls under the P distribution, the truth distribution, as in the, oh, well, this is the stuff that should be successful. It's where they overlap. That's where it should be true. Okay. And then next to it is the yellow region. That's actually your area of beta. Just like when we were looking at the legal example, this is your type 2 area of, oh, well, I'm in the region where you should fail to reject your null hypothesis, but you shouldn't have because it's false. And that's how these two look. So as you look at these, they're both tails of two different distributions, the one that's the truth and the one that's the hypothesized value. And as you look at this, one thing to keep in mind is the only way you can make these both be smaller is to actually increase your sample size, because increasing your sample size, I have the calculation for this spread on the side, reduces your spread of your distribution, and therefore your tails are thinner, not fat, and therefore have less area in them. So increasing sample size, that's increasing n, which means you divide by something larger, which makes your spread smaller. That's the only way to fix this. So again, reduce both types of error. The only thing you can do that is to collect more data, get a bigger sample. Let's do an example. Okay, so suppose a company that sells eco-friendly products is concerned that only 19.5% of people who use such products select their brand. A marketing director suggests that the company invest in new advertising and labeling to strengthen its green image. The company decides to do so in a test market so that the effectiveness of the marketing campaign can be evaluated. So we're going to look at the null and alternative hypotheses for this example and talk about what the type 1 and type 2 error could be and what their impact would be on the company. So our null is that the proportion actually is the 19.5%. An alternative is we think we've increased the market. We want it to be larger. We want more people to select our brand. So remember, the type 1 error is going to be, I am going to reject a true null hypothesis, which means this was true and I rejected it. So that would mean that I actually think that the brand has increased its customer footprint or it's got more sales when it actually really hasn't. And the impact of this is that you've wasted money on a marketing campaign that does nothing and you think it's done something. Sadness. Let's look at what a type 2 error would be. So remember, the type 2 error is going to be when you take a null hypothesis and you retain it even though it's false. So back to the null was that it's the same. So you're retaining something that's absolutely not true. So it's actually not equal to 19.5%, but you think it is. So the type 2 error here would be to think that, you think you've increased the percentage of customers buying the brand when in fact it has. So it's weird because you've missed an opportunity to increase the percentage of buying habits because you think the null is true. The null just says nothing's changed. So you maybe don't run the campaign anymore and it actually would have made a difference in your sales. Sadness. Let's talk about power. We can never prove the null hypothesis is true. This is something I've said a million times. You do not get to prove the truth. You can't handle the truth. It's not going to be the truth. It's the end. Well, I'm not at the end, but you know what I mean. So remember that the power is the opposite of making a type 2 error. So it's the probability that you don't do a type 2 error or you don't reject a false, or you correctly reject a false null. So it's like negate the type 2 error statement. The only way you can really fix this and make it so that you have a greater power is to increase sample size, because that is the only thing that will decrease beta effectively. And here's sort of the catch-22 about this. You might think that, oh, well, I'll just reduce my effect size And that's a bit of a problem. If you've looked at the animation, when you get your hypothesized value closer to the truth, so you've done a good job of estimating, your power of your test actually increases. And so does your, decreases, and actually causes your likelihood to make a type 2 error higher. So the closer you are, the more likely you are to make the worst decision. And the further you are, the greater the power. So that's a little bit scary. Yikes. But it's true. So how can we decide what power I may need? The power choice is really more of a financial decision than a statistical one. Power is calculated based on effect size, so it depends on how effective you want to be, and it's not generally easy to calculate. So I've done lots of power calculations on lots of different types of tests in my life, and they are usually quite unique every single time. You don't know ahead of time what the population proportion is going to be. You can only estimate what you think the power is going to be and what you think beta is going to be. So if you've logged into Minitab and went looking for the power tab, it's on there, but it requires a lot of guesswork to use it. It's not the best tool in the world. So here's one way you can reason your way through power. We're going to graph it. So if you can also watch the animation to see how this is going to work. So we're going to look at larger effect size and see how that changes everything. And we're going to be doing a right-tailed test for this one. The right tail is a little bit easier to visualize than all the others. So here's a look at what the power is. So power is actually the green region. I have two green regions on here because I stole this image from your textbook. I didn't steal because I just cited it, and it's also cited down here, so I'm not cheating. I'm also not being academically dishonest. So look down here. This region's power. I also labeled it, so that helps. So the idea is that alpha, that's your region of, oh, I reject my null hypothesis. This stuff over here is going to be, I failed to reject my null hypothesis. I got a lot of area, da 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 da. So the distribution on the top is what I'm calling the null hypothesis is true distribution. This is the one that is assuming that the P0 from your null hypothesis is the one making your distribution. So there's your P0. Down below we have what we've been calling the truth distribution. You know, the one that's based on the P, the actual proportion in the population, the one we don't know. Okay, we're going to pretend we know what it is. So we look at the critical value for alpha and draw it down here. And if you look at the values for P that you get, so if you picked anything in this region, you would have gotten something, you know, that was true because it's close to this P, but it's in the, you know, fail to reject region for the P0 distribution. So you would fail to reject that null. Oh no, but you shouldn't have. That's why it's a type 2 error. Similarly, if you look at alpha, that's the, oh, I'm going to reject it, even though it fell within the values of P that were correct. So it was true. So there's your type 1 and type 2 error and how they line up together. So if you picture moving this around, that's changing the effect size. So if we made P0 closer to P, imagine sliding this, you can see this on the animation. As they get closer together, alpha gets larger and so does beta. So this line stays fixed. As you move these closer, these values get larger. So the closer you are, the more accurate you are in your effect size, the more error you are likely to make. Uh-oh, that's unfortunate. The other thing that's bad about this is, well, when you look at the effect size, the further you are away, you're making a bad estimate, but you're less likely to make an error. You're more likely to make the right decision. So when it comes to power, it's not making the type 2 error. I said that already. Oops. Okay, well, unfortunately, finding power and having good power is not an easy task to get. And, you know, you really have to know what beta is to be able to hypothesize it. And you also have to know the true value, which we're probably never going to know. So again, we're looking at that same model for the upper and lower value, and the idea might be, oh, well, if I can control alpha, well, then I'll make alpha smaller, and that'll move my critical value. Okay, so I'll make less type 1 errors, but if you do that, you know, you get the following. You end up with a P star that's further over, and that gives you more beta, increases your type 2 error. Well, that didn't seem like a good fix. Okay, well, let's make our stuff more accurate. If you shift over P0 so that they're closer together, you increase both errors. How do we fix this? Well, I told you, the only thing you can do to really fix this is to increase the sample size. So if you increase the sample size, you end up taking the square root and all that stuff, and it's in the denominator. And you got to be careful, because in order to half your spread, you have to quadruple your sample size, and that's just not very cost effective. And it also reduces your tails, and then you get something that looks like this. So smaller spread, less error. That's the only way to really fix this, because notice these have smaller tails and they're fatter in the middle. This is exactly what it looks like when you use the exact same graphing that I did before, but with a smaller spread. It's the only thing to reduce errors. So when in doubt, sample large, That's not a new idea. And this is me saying the same thing I just did. Hey, if I want to reduce both my errors, larger sample size is always better. So when you're designing your experiment, you might want to calculate alpha or beta, doing like a first test run, and then update your results and reduce your errors that way. Let's do an example. So suppose a researcher is developing a scanner for hidden weapons in an airport and has concluded that the new device is significantly better than the current scanner. He made that decision using alpha equals 0.05. Notice we don't have the p-value. Suspicious. Would he have made the same decision at 10% level? How about at 1? Let's explain. So yes, at 10% he would have, because if you're going to make that decision at the 5% level, you're saying, oh, it is better. So you must have been in not the standard modus operandi mode, so not null hypothesis. So you were definitely rejecting. So if you're rejected at 5%, you're going to reject at 10%. Similarly, would you reject at 1? I don't know. You don't know the p-value. You just know that it's smaller than 5%. And not every value that's smaller than 5 is going to be smaller than 1%. But everything that's smaller than 5% is smaller than 10. That's the difference between these questions. So, you maybe would have made the same decision. Can't tell. Who knows? How about another example? A bank wants to know if the enrollment on their website is above 30% based on a small sample of customers. They test the null hypothesis, being that the proportion of customers enrolling on their website is 30%, and suspect the alternative is that it's actually greater, and end up rejecting this hypothesis. Later, they find out that the actual percentage is like 28% of customers enroll that way. Did the bank make an error? If so, what kind? I hope you're looking at this and thinking, oh, this looks kind of wrong. They rejected. And so they said it's not equal to. It's small. And I don't know. Let's see. Okay, getting too excited about this. Yep. They concluded that actually it was more than 30% and it actually was smaller. So they actually looked at a null hypothesis and rejected it when they really shouldn't have. So they actually made a type 1 error because they rejected a null hypothesis incorrectly. Not because that null was true, but because they rejected something they shouldn't have. So be careful. Alrighty. Let's go to our summary. What can go wrong? Don't confuse proportions with means. The big difference between proportions is they come from categorical variables, and means come from quantitative. You should be able to tell the difference between these two variables because quantitative has units. Categoricals do not. So you may have gotten used to the idea that numbers means that it's numbers means that it's quantitative, but that's not true. Zip codes are numbers, and they are not quantitative. They are categorical. They tell you what region you live in, which is very much categorical, not quantitative. So be careful. Make sure you're doing the right test. If you're not sure, watch my video on the summary of doing all the tests at once. It will help you. Don't base your null hypothesis on what you see in the data. Don't do that for your alternative either. And don't make the null hypothesis what you want to show. This is all just bad sciencing. It's, I'm going to make this be what I already saw, or I'm going to make this look like what I think it's going to be, not, I'm not sure what this is going to be. This is my instincts. This is something I can prove or disprove. You're not making a claim. You're back wizarding, which is just, only I get to be a wizard. Always, always, always check your conditions or check yourself before you wreck yourself, because that's just wrong. You shouldn't be using something if you don't know that you can use it. And don't pay attention too much to alpha. I know that it gets hammered into your head, stat 1. don't listen to it. And be careful about practical versus statistically significant, especially as you go out into the working world. Not so much for us, but it's going to be important when you go to apply this to your own jobs. Um, and I hate to say this, but you need to be comfortable with your wrongness, which is also life advice, not just statistical advice. Be comfortable with the fact that no matter how careful you are, you might still make an error, and that's not your fault. That's the data working on you. Okay, so we talked about p-value at length. I am not reading this to you. You should take a look at it. It's just reiterating all the understandings of what a p-value informs you of. This is the new stuff. Beware of the two types of errors. Make sure you know them in detail and how to describe them for specific situations. Make sure you understand the power of the test is actually a probability calculation, and it's very affected by effect size. However, the only way you can improve power calculations and along with error is to make sure that you change your sample size, aka increase it. That's all I have for you for now. May the power be with you.